multiplicity when we combine two systems? Who wants to guess? If you have multiplicity of system A and you have multiplicity of system B, and there's an operator between them, what do you think it is? Love it, times, it's the right answer. Okay. But to think through it quickly, we'll go like this. So here we have system A. This is one of the configurations of system A. And that configuration, when it combines with B, it could combine with any one of B's different microstates. Okay? Then, now we have our second possible microstate of A. This one could combine with all the different possible microstates of B. And we have all the possible microstates of the next one for A, all the ones of B, the next one of A, all the ones of B. And so this is how we come to the combined multiplicity is going to be the product of the individual multiplicities. Okay? So we call this an additive property. The product of the two is an additive property. Okay? So multiplicity is an additive property. It's also an extensive property. What does extensive mean? It depends on size. We just showed that when the volume doubles, multiplicity went up. It was dependent on size, right? Okay, so other things that depend on size, volume, energy, an intensive property were things like temperature and pressure. So multiplicity, I have system A and I have system B. And when they come together, the combined multiplicity will be the multiplicity of A times the multiplicity of B. Okay, and if I take the natural log of both sides, the natural log of this multiplication, kind of going the other way with our properties of logs, you can split it back apart and do the natural log of A plus the natural log of the multiplicity of B. Okay, and then here for extensive, this is really, in this case, I've doubled the size of my system, but it would almost be like adding multiplicity 1 to multiplicity 1 again, right? So here it's raised to the 2, but it's the same as these two things being multiplied by one another. Okay, this is another property of logs that I did write out at some point, but it's here again. An exponent comes down into the front. Okay, move the 2 into the front. Why was Boltzmann using natural log of W in his definition of entropy instead of just multiplicity? This was a quiz question for anyone that did this one. Okay, there are at least 2 reasons because I asked for 2. What's the easiest one? Okay, say that again? Okay, sure, yes. We're going to have to use the Stirling approximation eventually. You'd have to use some approximation, it might not be Stirling's, but eventually you'd have to approximate no matter what. But yeah, that's good, because we're going to learn a new definition of entropy today called probabilistic, and in the end it boils down to Stirling, really. Yes, or Faith, or whoever.
Because it has like the same general curve shape and the same maximum. Yes,
so satisfying the maximum entropy principle was key, and the other thing was the numbers are just way easier to work with, right? Okay, so we have way smaller numbers, and then also the function itself, okay? Multiplicity has sort of a curve that looks normal, and then as you add more and more and more numbers of trials, if things were 50-50, you're gonna get a really strong peak right at the center, okay? The top of which, I did read someone's quiz where they were just like, they both have a flat top, and I'm like, ooh, I know what you mean there, but I don't know if I can give full credit to flat top. I need you to say, you know, like the slope is 0 at the maximum or something like that. But yes, it is a function that still satisfies the maximum entropy principle will have 0 slope. So recall that for independent events, the combined probability is simply the product of the individual probabilities, right? This is our AND statement, our multiplication rule. So the same thing is applying with multiplicities. Okay, entropy, however, of a combined system is going to be the sum of the individual entropies. And so logarithm is also an important choice because it satisfies these 2 conditions. Okay? And so this is showing you here If you have S total is equal to Boltzmann's constant times the natural log of the total multiplicity when you've combined two systems, this would be equal to Boltzmann times the natural log of the product, multiplicity A times multiplicity B. Okay. We know by properties of logs we can then pull this apart and have Boltzmann's constant times the natural log of multiplicity B, Boltzmann's constant times the natural log of multiplicity A, and this is just the entropy of A. This is just the entropy of B. Okay, so natural log also lets us satisfy this condition. Give you a second to write those equations down. Write them down, because we're going to stop and do a practice problem while I have to use it. You will get, again, a new equation sheet before the midterm that has all of the things I would need you to use on it. But it's not ready. So what was the other entropy definition that we know already? In addition to statistical, we have one other one. You either say the equation to me or maybe the name of it. What would you call it? Okay, Q reversible over temp is equal to what? Change in entropy, delta S, right? And so we call this the thermodynamic definition, the classical definition are some of the words that I would use, right? Okay, so if you go into pages 327 through 331 in your book, they go through the entire proof that these two things are equivalent, okay? We were looking at a 2D grid box. In reality, they'll actually show you for 3D volumes, okay? If you had a tiny little 3D volume, as you expand, what's happening with heat, what's happening with multiplicity. It's beyond the scope of what we have time for, but if you are interested, I recommend looking at it, or if you just want to get extra practice with these two equations. It also introduces another form of Stirling. Okay, we saw natural log of a large factorial was equal to that number n times the natural log of n, and then minus n was a correction term. This introduces a new version of Stirling that I haven't bothered to teach in the past. It's relevant to chemical potential in chapter 10, so we may do it next Thursday. So if you want to look at it now. And then the one thing I'm not going to go through this one in the interest of time. I'll give you the full solution online. I have it written out here. But let's just stop and think about it for a second. A system starts with a multiplicity of 20,000, so this is W initial, let's say. 2 kilojoules of heat are transferred into the system reversibly. Okay, so we have Q reverse given to us. We have a temp, 298K. What is the new multiplicity? So this is a book problem. Okay, so it's asking you for W final. Okay. And we have Q reversible in a temp, so we should be able to get a change in entropy. And then from that we can get entropy initial, and we already have our initial multiplicity, so we'll be able to get entropy final and then calculate multiplicity final from it.